Hi, I'm Andy and welcome to my walkthrough of the 2020 Sans Holiday Hack. In this video we're focusing on objective number 9, where we need to regain control of a compromised machine. But first, Alabaster wants us to run through the Scapy Prepper terminal, which is probably handy as it sounds like this tool is needed for the main objective, and it's something which I personally have not really used much before. Scapy is a Python library for capturing, creating, modifying and transmitting individual packets, and is a fantastic tool for low-level network hacking. The Prepper terminal asks a series of increasingly difficult questions. Question 1 is just to call the task.submit function with the string start to make sure we know how to submit future answers. Question 2 asks for the name of the Scapy function that sends packets out onto the network. This is just send. Likewise, question 3 asks the name of a function for sniffing packets, which is sniff. Next, some multiple choice. Which one of these would send a packet and then capture the next one it receives? That's the SR1 function, so the correct answer is number 1. Question 5 wants to know the function used to read packet capture files into Scapy. That'd be rdpcap, short for read pcap. Next up, how would we print a summary of the packets contained within the variable UDP packets? That's achieved with the show function like this, so the correct answer is number 2. Question 7 digs deeper. How to show details of the first packet. We can call the show function of a specific array element for more details like so. This particular packet appears to be part of a DNS request, and we can see the various encapsulation layers of UDP, IP, and Ethernet above. After submitting the first packet, question 8 asks for just the TCP layer of the second packet in TCP packets. We can get a summary view with .show, which suggests that these packets are part of an FTP connection. We can drill down further into the details of the second packet at index position 1, but to only show the TCP layer, we must additionally specify this like so. In question 9, we're asked to change the source IP of a packet and submit the resulting packet. Changing data is a simple assignment like this. Question 10 wants to know the password for the FTP connection we saw. The first 3 packets contain the SYN, SYNAC, and ACK of the TCP handshake, so there's not going to be any data of use in them. Digging deeper into the fourth packet, at index position 3, reveals a lot of info, but we're only interested in the payload, so we can be a bit more specific like so. We can then iterate through to witness the exchange of messages between server and client, culminating in the password echo, which can then be submitted. We get a little reward for completing this question, a better way of extracting payloads into an array in just a single statement, which could be very handy if there were many more packets to work through. But onwards to question 11, which asks for the checksum from the second packet in ICMP packets. Note that there's 2 checksums present in this packet. The first is just the checksum for the IP header, but the question wants us to submit the checksum of the ICMP layer. Next, another multiple choice question. How do we create an ICMP echo request packet? That'd be option number 3. Question 13 asks us to create a packet with specific properties. We can follow a similar format as that given in the possible answers for the previous question, specifying the IP address within the IP layer and the destination port within the UDP layer. The next question wants another packet crafted, this time a DNS request. This requires a little more detail and reference to the Scapy documentation, as the request itself is formulated with an additional DNS QR or DNS query data structure like so. The final question asks for a few fields in an ARP response to be set to the correct value. There's 2 packets in the ARP packets array, and we can get some further info on the first. This is telling us that the machine with IP address 192.168.0.144 has MAC address 0016CE6E8B24, and wants to know the MAC address of IP 192.168.0.1. The destination MAC is all Fs, This is the broadcast address, so this packet would be received by all hosts on the local network. The second packet has most fields completed for a successful ARP response, however, the hardware source, hardware destination, and op fields are all missing in the ARP layer. The first two are already available in the Ethernet header of this packet, so just need to be copied over into the ARP layer. After a quick check of some reference material, the op code for an ARP response is 2. Let's verify our changes, and submit. With the Scapy Prepper terminal now complete, we can chat with Alabaster again. He provides a little more detail on the main objective, and some hints. Accessing the terminal for the main question requires Santa mode, so a quick hop through the painting later, we get stuck in. Jack Frost has hijacked the host at 10.6.6.35 with some custom malware, which is then attempting to retrieve a follow-up payload. We're tasked with taking back control of this machine. Apparently, the help.md file has a little more info to help. The hints from Alabaster suggest that this malware is trying to pull a Debian package, although with a challenge named ARP Shenanigans, it's likely we'll need to do some ARP spoofing. Let's take a look at what's happening on this network using TCP dump, with the -E option to also include details of the Ethernet layer. As expected, there's a periodic stream of ARP requests as the device at IP address .35 tries to find the MAC address for .53, but nobody is responding. Well, if nobody else is going to claim that IP, we can. We just need to reconfigure our network interface, although this is likely to fail as we are but a guest user. Yes, it fails. It looks like we'll have to use our newfound Scapy skills to craft an ARP response packet to trick .35 into believing that our machine has IP address .53. To help, this machine has some example PCAPs of ARP and DNS traffic. Let's fire up Scapy and dig into the ARP PCAP. Comparing each of these packets side by side is handy to clarify which bits of data belong in which fields without having to Google for any reference material. Specifically that in the response, HW source and P source relate to the answer of the query. Also provided on this machine are a couple of strawman scripts which are pre-configured to capture ARP and DNS requests. To use this to spoof an ARP response, we must add some code to craft an Ethernet packet of our choosing. The destination MAC will be that which is the source of the request, and the source will be this local machine's MAC. Op is set to 2, representing an ARP reply as opposed to a request. P-type and HW type are set to hexadecimal 800 and 1 respectively, the identifiers for IP and Ethernet protocols. P-len and HW-len are set to 4 and 6 respectively, these being the lengths of an IP and a MAC address. Next, the source and destination MAC and IP addresses are set. Finally, the ARP layer and Ethernet layer are stitched together, and the response pushed out over the network interface. Let's set TCP dump running again in a separate window, and launch this script. The ARP spoofing appears to work as we now receive a DNS request addressed for 10.6.6.53. Then ARPs continue. It's worth noting that the target machine and any others on the network would normally cache the ARP response, and therefore we'd not typically expect to see repeated ARP requests. However, this is a CTF and it looks like this is simply part of the engineered design. Those continuous ARPs are a bit annoying, so we can filter them out by adjusting the TCP dump parameters as follows. The target machine wants to know the IP address of this domain. So we just need to repeat the same trick, but this time crafting a DNS response instead of an ARP response. The goal is to tell the target machine that the DNS name that they want to reach is actually our own machine. Again, the strawman script makes this a bit easier and operates in essentially the same way as before. Sniff a single packet, send a response, and then exit. We'll start by making a note of the IP address that we're pretending to be, 10.6.6.53. Next, set the source and destination addresses at the MAC and IP layers, and the port numbers at the UDP layer. Then, at the DNS layer, which is a little more complicated, RD is set to 1, matching that from the request packet. QR is set to 1, signifying that this is a DNS response, not a query. The QD data structure is copied over from the DNS request. This contains the DNS name and record type being requested. The AN section is a new DNS resource record data structure, or DNSRR, containing fields mainly copied over from the request again, but here the RData field is set to this machine's local IP. These layers all get wrapped up together and sent out over the network. Let's give it a try, launching both scripts one after the other. The second script doesn't seem to be detecting the DNS packet. It seems like the DNS request is appearing on the network before the DNS response script has a chance to start up properly. So instead, let's launch it in the background, ready and waiting for a response, and then launch the ARP spoof. This now works as expected, and we see a bunch of packets transferred. It'll probably be useful to analyze this in more detail, so let's reconfigure tcpdump to capture them to a file, and rerun the ARP and DNS spoof. Now to fire up Scapy, import the capture, and investigate the contents. Some data is being sent to .35 by our machine. This seems a bit odd and the contents don't make much sense, but maybe we'll come back to that later. For now, the last few packets are the most significant. They show the target machine now attempting to reach out and establish an HTTP connection with our machine off the back of that spoofed DNS response. But, as there's currently no web server running, the connection is rejected. We can fix that by spinning up a quick Python-based web server, which will serve up any files placed into the web folder. Now to launch the attack again, and this time observe what resource the target machine is trying to obtain. It's trying to grab a Debian package called survived_amd64.deb from the pub jfrost backdoor folder. It seems like whatever Jack Frost has done to compromise the target machine, it's now trying to download the next part of a backdoor payload. But now we're pretending to be his web server, and we can serve up our own backdoor package to regain control of the system. Instead of creating one from scratch, it's possible to take an existing package, extract the contents, modify it, and then wrap it back up again. And this system helpfully has a few Debian packages available on it already, including a package for netcat. This seems like a perfect target. We can install the netcat binary and then use it to create a reverse shell. First, to extract the contents of that package using the dpkg-deb tool. Within it, there's a file called postinst. This script is run once the package has finished installing. It currently contains a few commands to set up some symbolic links, but this is a great place to add the reverse shell. We can confirm the IP address of our machine with ifconfig, and then add a line in the postinstall script to launch the newly installed netcat, attach it to a new instance of bash, and connect the other end back to our machine. I'm choosing TCP port 1690. Now to repackage backup with dpkg-deb, ensuring it has the right file name, and then copy over to the correct folder within the web root. Now to put all the pieces of the puzzle together. The web server continues to run and respond to requests. A reverse shell listener can be started with netcat. And then the ARP and DNS spoofing scripts launched. They take effect, and the target machine retrieves our own backdoored package from the web server. And, once it's finished installing, we see confirmation that the reverse shell has connected. To prove that we have successfully taken back control of this machine, we were tasked with retrieving a text file from the root of the file system that contained board meeting minutes, and stating who recused herself from the vote described in the document. The minutes describe 2 orders of business, one relating to a new furnace being installed by Mr. Miser, which could burn down the North Pole, something that he seems to revel in. The proposal is rejected, although it wouldn't surprise me if Mr. Miser ends up causing further trouble in a future holiday hack. The other item relates to a disagreement over the planning consent for Santa to increase the size of his castle, with Jack Frost in particular complaining about its impact. Perhaps this is what has driven him to sabotage Santa's operation. Regardless, we see that it was Tanta Kringle who recused herself from the vote. Once entered into the badge, this objective is complete. That's all for this video, but leave a comment if you have any questions or if you used a different method for solving any of these puzzles. We'll pick up the story in part 10, where we'll be hacking the Santavator to bypass a fingerprint reader. Feel free to take a slight detour on your way and check out some of my other cybersecurity videos, otherwise I'll see you there.